Welcome back to The Deep Dive. We're the show that really tries to pull out the key insights from the latest research so you get informed quickly without getting, bogged down.
Exactly. Straight to the good stuff.
And today, we're plunging into something pretty fascinating. Advanced AI agents.
Mm-hmm.
We're not talking about your standard chatbots here.
Yeah.
We mean those really ambitious systems, the ones designed to tackle complex, multi-step problems, like in the real world.
Yeah, think about an AI that doesn't just spit out text, but can navigate environments, perform tasks, learn. Truly autonomous agents.
That's the grand vision, right?
It absolutely is, and it's vision that could change, well, almost everything. Robotics, automation, even how we do science.
But, okay, there's always a but. What's the catch with building these super agents?
Well, the big challenge is that even when these agents succeed, and they can succeed, they often do it in ways that are, well, surprisingly inefficient, sometimes illogical. We often call them brittle paths.
Brittle, meaning they break easily.
Sort of. It means they might work for one specific scenario they were trained on, but fail with slight changes. And the core issue, the real elephant in the room, is this thing called inefficient exploration.
Okay.
See, traditional reinforcement learning, which is super powerful, don't get me wrong, it often just pushes the agent to find any way to win. Any path to success gets rewarded.
Even if it's a crazy roundabout path.
Exactly. Even if it's full of redundant steps or illogical moves or things that just waste time in computation, if it eventually gets the job done, boom, reward.
Ah.
So it begs the question, are we actually training these agents to think and solve problems well? Or are we just teaching them to stumble across solutions through sheer persistence? Maybe just getting lucky.
That inefficiency sounds like a huge roadblock then. If you want something truly reliable, you can't have it just getting lucky.
Precisely.
What happens when an agent needs to genuinely reason through a task step by step like a person would?
That's the crux of it.
And this inefficient exploration, this is exactly what a new framework is trying to tackle, right? Something from Hunyuan AI Digital Human at Tencent.
That's the one. They've introduced RLVMR. That stands for Reinforcement Learning with Verifiable Meta-Reasoning Rewards.
Okay, that's a mouthful. What's the core idea?
The core idea is pretty fundamental. It's about teaching the AI agent how to think more coherently, more efficiently. Not just rewarding the final what, but improving the how.
A shift in philosophy, really.
Significant one, yeah.
And that's our mission for this deep dive. We're going to unpack the tech behind RLVMR. How does it actually get around the problems with older methods? What does it mean for building agents that are, more robust, more general?
That's the plan.
Yeah.
We'll focus on the technical nuts and bolts, the performance gains.
Exactly. As always, we're keeping it technical, looking at the capabilities and the implications. So let's get started.
Let's do it.
So let's really dig into this inefficient exploration problem first. You said agents find successful paths, but the reasoning during the path is flawed. Can you elaborate? Why is that such a big deal for these complex, long-horizon tasks?
For sure. So imagine you have a large language model trying to do something with many steps. Maybe navigating a virtual house, finding objects, putting them somewhere specific.
Like a household robot simulation.
Exactly. Traditional RL, as we said, mostly cares about the end result. Did it succeed? Yes. Okay, here's your reward. But that reward often comes only the very, very end. It's sparse.
Right. Not much feedback along the way.
Precisely. And that sparse signal doesn't tell the agent anything about how it got there. Was the path smart, efficient, logical? The reward doesn't care.
So it could just stumble around?
You could stumble upon a sequence that works, totally by trial and error. But maybe half the actions in that sequence were pointless, redundant, illogical, like going back and forth between two rooms unnecessarily.
I think I've done that myself looking for my keys.
We all have. But for an AI, it means the learned strategy, the policy, is brittle. It works for that specific training scenario it stumbled through.
Ah, but change things slightly.
And it falls apart. Because the underlying reasoning process isn't sound. It hasn't learned a general principle of how to solve the task. It's just memorized a specific, potentially flawed sequence of actions.
It's like you showing someone a very specific route on a map, but they don't learn how to read the map itself.
That's a great analogy. They can follow the line, but put up a detour sign, and they're lost. They haven't developed that robust internal model of how the world works or how to solve problems generally.
Just memorizing what worked before in one case.
Right, and there's good evidence for this. The paper has this really clear example using an agent trained with GRPO, that's the standard RL method, in this simulated world called ALFWorld.
ALFWorld, the household tasks 1.
Yep. And the agent's task was put 2 keychains in the safe. Simple enough.
Sounds simple. What did the agent actually do? This is where it gets interesting.
It really does.
Yeah.
So by step 7, it had managed to get to dresser 1, and it picked up keychain 1. Okay, good start. Sub-goal achieved.
Progress.
But then its internal thought process, or what the model generated as its reasoning, said it still needed keychain 2 and then needed to go to the safe. Logical next steps.
Okay.
But the action it took, go to dresser 1.
Wait. It was already there. It just picked something up from there. Why go back?
Exactly. That's the inefficient exploration in action. And it wasn't just once.
Oh, no.
It tried go to dresser 1 several times in a row. And each time, the environment observation was basically nothing happens because it was already there.
It's like pushing on a door that's clearly marked pull.
Right.
Repeatedly.
Pretty much. Then eventually it tried move keychain 1 to safe 1, which also failed because, well, it hadn't found keychain 2 yet and it hadn't even opened the safe. Again, observation. Nothing happens. It was stuck, utterly stuck in a loop.
Wow, that image is vivid. Constantly checking your pocket for keys, you put in your bag. Why do they get stuck like this? What's missing?
What this shows is that the agent's learned strategy, its policy, it's really just reflecting the patterns it saw in training data. It's not based on a real understanding of its current situation or self-reflection.
So it saw go to dresser 1 lead to good outcomes sometimes in the past.
Possibly. Somewhere in its vast training history, that action might have been part of a successful rewarded trajectory. But the sparse reward doesn't give it the fine-grained feedback to say, hey, doing that right now when you're already here is pointless.
It found a statistical correlation, not a causal understanding.
That's a good way to put it. The traditional training just doesn't penalize this kind of obvious redundancy effectively. It wastes steps, wastes compute.
Okay, so that's a qualitative example, but the paper backs this up with quantitative data too, right? They used ALFWorld and also ScienceWorld.
Yes, ScienceWorld involves text-based scientific experiments, another complex domain. And crucially, they use these generalization splits to test adaptability.
Right. L0, L1, L2. Can you remind us what those mean?
Sure. L0 is basically seen stuff tasks, very similar to training. L1 introduces unseen variations within familiar categories. So maybe a different object to find in the same type of house layout.
Bit of the novelty.
A bit. But L2 is the real stress test. Unseen variations and unseen task categories. Totally new situations. This really measures if the agent can generalize, if it's truly learned to problem solve.
And they tested 2 main baseline methods against these splits.
Yep. First, supervised fine-tuning, SFT. That's basically showing the agent lots of examples of an expert doing the task correctly and telling it do this.
Learning by imitation.
Exactly. And second, group relative policy optimization, GRPO. That's the end-to-end RL approach we mentioned, optimizing purely for the final win.
Okay, so what did these baselines reveal about the core problem? How did SFT do?
SFT looked pretty good at first glance, especially in the scene tasks, the L0 split. For instance, they used a model called Quen7b. On ALFWorld L0, it got a 63.3% success rate, and it was efficient to very few invalid actions, like only 6.2%.
So good at copying the expert on familiar ground.
Very good. But that efficiency was incredibly brittle.
Ah, here it comes.
When they threw the unseen L2 tasks at it, the success rate for that same 7B model just tanked, down to 37.5%.
Yeah, big drop.
Huge. And even more telling. Look at the repetitive action rate. On L0 is about 14%, but on L1, just unseen variants of seen tasks, it almost doubled to 24.5%.
So faced with little novelty, it just starts repeating itself.
Exactly. It falls into these unproductive loops. It shows SFT teaches agents to mimic actions in specific contexts, but it doesn't instill a robust, adaptable reasoning process. It doesn't know why the expert did those things.
Like that robot tracing the path. Hit an obstacle, it's lost. Lacks understanding.
Precisely. Now, GRPO, the RL method, different story.
Better generalization, I imagine.
Much better. The 7B GRPO model hit 77.3% on L1 and 52.3% on L2. Way better than SFT on the unseen stuff. Because RL inherently explores more, tries different things.
Okay, so it adapts better. But what's the cost? You mentioned inefficiency.
Severe inefficiency. That's the trade-off. The paper highlights really high, invalid and repetitive action rates for GRPO. Remember that L2 split where it got 52.3% success?
Yeah.
Its repetitive action rate was a staggering 31.2%.
Almost a third of his actions were just repeats.
Yep. It confirms that whole inefficient exploration idea perfectly. GRPO optimizes for the final goal, so it reinforces any path that gets there, even if it's ridiculously wasteful or illogical. The agent hits the goal, gets the reward, and learns, okay, that crazy pass worked.
Yeah.
It doesn't learn to avoid the waste.
So GRPO is like that person finding their way through the maze eventually, but only after hitting every dead end 10 times.
Great analogy. It gets there, but oh, the journey. And here's another kicker. Just making the models bigger doesn't fix it.
Really? I thought bigger models were always better.
Not necessarily for reasoning efficiency. They tested models from 1.5 billion parameters up to 7 billion. The 7B GRPO model got higher L2 success than the 1.5B model. Sure, 52.3% betas, 29.7%.
Okay, so bigger was better for success rate.
But the 7B model also had a higher repetitive action rate, 31.2% compared to 27.1% for the smaller 1.5B model.
That's backwards. How?
It suggests that the larger models, with more capacity, might actually get better at exploiting these flawed, inefficient strategies. They have more power to find and stick to these roundabout paths that eventually work.
So they double down on the bad habits.
Kind of. It implies the limitation isn't just model size, it's the training objective. The reward signal itself is reinforcing the wrong kind of process.
That's a huge point. It's not just scale, it's how you teach them. The learning signal is flawed.
Exactly. So you're stuck with this dilemma. SFT gives you brittle efficiency, fast but fragile. GRPO gives you inefficient generalization, adaptable but incredibly wasteful.
A classic trade-off. And that's exactly where RLVMR steps in, trying to break that trade-off.
Precisely.
Okay, so if the problem is that agents aren't learning how to think efficiently, RLVMR takes inspiration from metacognition. Thinking about thinking. That sounds deep.
It is pretty deep, conceptually. Metacognition is our human ability to reflect on our own thinking, to plan, monitor our progress, adjust our strategies when we hit a wall.
Like realizing you're stuck on a math problem and deciding to try a different approach.
Exactly that. It involves knowing your strategies, metacognitive knowledge, and actively managing them, metacognitive regulation. The paper argues that for LLM agents to really crack these complex long-horizon tasks, they need more than just knowing facts. They need dynamic planning, self-monitoring, and crucially, creative exploration when things go wrong.
An internal compass, not just a map. So how does RLVMR actually build this into an LLM? It's not like you can just tell it be more metacognitive.
Right. They operationalize it. RLVMR builds on the React framework. You remember React. It interleaves reasoning steps like thoughts with actions.
Yeah, the agent thinks aloud before acting.
But often, that thought in React is just one big chunk of text. RLVMR refines this by introducing structured meta-reasoning tags, little labels within the thought process.
Tags like XML tags.
Kind of, yeah. These tags explicitly mark different kinds of cognitive functions. This decouples the reasoning from the action and makes the internal process transparent and, critically, verifiable. You can see what kind of thinking the agent is trying to do.
That's clever. Breaking down the thought blob. What are these tags?
They define 4 key ones. First is planning.
Okay, planning makes sense.
Used at the start, or when the agent needs to rethink its whole strategy. It's for breaking down the big goal into high-level steps. Like for our keychain task, planning step 1, find keychain 1. Step 2, find keychain 2. Step 3, go to safe.planning, outlining the whole sequence.
Setting the overall strategy, looking ahead.
Exactly. Then there's explore.
For when it gets stuck.
Pretty much. Or facing uncertainty. It encourages generating new ideas, trying different options, looking for information. If it can't find something, it might output. Explore keychain not here. Maybe check the other dresser. Or the table.explore. It pushes for creative problem solving, actively fighting against just repeating failed actions.
Ah, directly tackling that repetition problem. Nice. What's next?
Third is reflection. This one is huge for learning from mistakes.
Self-correction.
Precisely. It gets triggered after failures or unproductive steps. The agent looks back. Reflection. Okay, trying to open the safe failed. Maybe I need the key first. Or is it unlocked? Let me check the task description again. That reflection. Analyzing what went wrong. Figuring out a fix.
Learning from experience, basically. And the last one.
Monitor. This is more for when things are going okay. It's about tracking progress against the plan, making sure the current actions still align with the sub-goals. Like monitor. Okay, got keychain 1. Plan says find keychain 2 next. Current location is dresser. Need to search elsewhere. Monitor. Keeping itself on track.
So planning sets the course. Explore finds new paths. reflection fixes mistakes, and monitor keeps it on track.
That's a great summary. And this is where RLVMR gets technically interesting. It's not just generating text, it's generating structured, categorized text representing cognitive states.
Yeah.
That makes the reasoning verifiable, and, this is key, makes it rewardable.
Giving the AI a structured internal monologue, a window into its mind, that seems vital for actually improving it, right? Not just hoping it gets smarter. So how do they train it to use these tags?
It's a two-phase process. Phase 1 is a cold start.
Cold start.
Yeah, initial meta-reasoning acquisition via SFT. It's a quick supervised fine-tuning step. The goal is just to teach the base LLM the syntax, how to generate these tags correctly, how to structure its output, like planning action.
Just learning the grammar of thinking.
Exactly. They use a tiny data set for this, only 200 trajectories. These are observation-action pairs. But they use a powerful teacher model, like GPT-4, to go back and infer the likely meta-reasoning tags that should have been there. Then they fine-tune the agent on these annotated examples.
So it's like showing a kid examples of well-structured essays before they write their own, giving them the template.
Perfect analogy. Bootstrapping the ability to express structured thought. And it's very lightweight, very efficient.
Okay, so it learns the grammar. Then comes phase 2, the main event.
Phase 2. RLVMR proper. Reinforcement learning with composite rewards. This is where the agent interacts with the environment and really learns.
And those verifiable meta-reasoning rewards come into play here. How do they work? How do they shape behavior?
This is the core innovation. They don't just rely on the final win-loss signal. They use a composite reward. Part of it is the traditional sparse outcome reward.
Win-loss signal, yeah.
Right, binary. You get a rewarders for success, 0 otherwise. Still essential for knowing the ultimate goal.
But the special sauce is the other part, the process rewards.
Exactly. Dense, process-based meta-reasoning rewards, RMRT. These are given at each step to encourage good thinking habits.
Like what?
Okay, so for a planning step, you get a reward planning, but only if the whole trajectory eventually succeeds.
Ah, so planning is only good if it leads somewhere useful.
Right. For explore, you get explore if the action targets a new object or location. Directly discourages going back to the same old dresser. Fights redundancy. And for reflection, you get irreflection if that reflection step leads to a corrective action after failures. It rewards learning from mistakes and changing tack.
So it's rewarding productive exploration and effective self-correction. Not just any thinking, but good thinking.
Precisely. And there's one more small piece. A format reward. Format. It's actually a penalty, like many 0.1. If the agent messes up the tags, forgets one, puts it in the wrong place.
Keeps the structure clean, makes sure it keeps thinking aloud properly.
Exactly. Ensures the whole process stays verifiable. So the total reward at each step T is the sum. RT equals RMRT plus R format.
Okay, that's a sophisticated reward signal, guiding the outcome in the process. How do they actually optimize the agent's policy using this complex reward? Does it need complicated algorithms?
They use something called group relative policy optimization with meta-reasoning, GRPO-MR. It's adapted from PPO, which is a standard, pretty effective RL algorithm.
PPO, yeah, heard of that.
A lot of RL algorithms, especially for complex tasks, need a separate critic network to judge how good actions are. That adds overhead. GRPO-MR is clever because it handles this composite reward efficiently without needing that separate critic.
Oh, that's good. More lightweight for LLMs. How does it manage to combine the final outcome reward with these step-by-step thinking rewards?
That's the key trick. It calculates the advantage for each step, basically, how much better taking that action was than expected by looking at both the big picture and the local reasoning quality.
Both global and local.
Yeah. Think of it like coaching again. First, there's the trajectory level relative advantage, a Troj K. That's like the final score of the game, did we win or lose? Normalized across a batch of attempts. Captures overall success.
Okay, the big picture result.
Then there's the meta-reasoning level relative advantage, AMRT tag. This is like grading specific plays. They take all the steps within a batch that use the same tag, say, all the explore steps, and compare their rewards within that group.
Ah, comparing apples to apples. Explore steps only get compared to other explore steps.
Exactly. It asks, how good was this specific explore attempt compared to other times we tried to explore? It gives much more targeted, fine-grained feedback on the quality of that type of reasoning.
That's really precise.
It is. And the final step-level advantage is just a weighted mix of these two, the global outcome and the local reasoning quality. They use a hyperparameter to balance them, setting it to 0.5 in the paper.
So half influenced by the final score, half by how well you ran the plays along the way.
You got it. The bottom line is, this combo pushes the agent not just to win, but to win smartly, to use verifiably good reasoning steps all the way through. It fundamentally changes the goal from just succeed to succeed intelligently and efficiently.
Building robust, intelligent problem solving right into the learning process, not just hoping it emerges. Okay, this sounds great in theory. Let's talk proof. The results section must be where this really comes together.
Absolutely, and the results are, frankly, quite striking. RLVMR consistently beats the baselines. All of them.
All of them, including other advanced methods.
Yep. Methods like ETO, GGPO, even comparisons against much larger models like GPT-4o, DeepSeek, Agent Gym using standard strategies. RLVMR comes out on top on both ALFWorld and ScienceWorld.
Give me some numbers. How did that Q7B model do with RLVMR?
On the scene tasks, ALFWorld L0, it hit 91.4% success. ScienceWorld L0, 67.2%. Very strong performance on familiar ground.
Okay, but the real test? Generalization. That tough L2 split, unseen everywhere.
Yeah, that's what's most impressive. On ALFWorld L2, the RLVMR trained 7B model achieved 83.6% success.
83.6%. Didn't you say the best baseline GRPO was only around 52%?
DRPO was 52.3%, yeah. And the next best after that, GGPO, was even lower. So RLVMR achieved a massive 16.4 percentage point jump over the strongest baseline on the hardest generalization test.
Oh, wow. That's huge.
It really is. Similar story on ScienceWorld L2. RLVMR significantly outperforms. It strongly validates the core idea. Rewarding the meta-reasoning process directly teaches the agent how to reason effectively, which translates directly into better generalization. It's learning the skill, not just memorizing answers.
Okay, this next result you mentioned earlier really caught my attention. Smaller models beating bigger ones.
Yeah, this is super interesting and potentially very impactful.
RLVMR lets smaller models punch above their weight. How much better?
Take the Qwen 1.5B model. Much smaller than GPT-4o, right?
Yeah.
Trained with RLVMR, that 1.5B model achieved 87.9% success on ALFWorld's unseen L1 split.
Okay. And GPT-4o, using a standard approach like React.
GPT-4o with React scored 66.0% on that same split.
So the 1.5B model with RLVMR crushed GPT-4o.
Crushed it by over 20 percentage points. It powerfully shows that targeted process-level rewards are a more effective and likely more efficient path to high performance than just relying on massive scale.
It's not just about brute force parameters, it's about smarter training.
Exactly. Quality of learning over quantity parameters, you could say. You're guiding the model to build a better internal reasoning engine.
That has massive implications for cost, for accessibility, making powerful AI feasible without needing giant models.
Huge implications. And this efficiency shows up elsewhere, too. RLVMR directly tackles that inefficient exploration we keep talking about.
Right, the looping and wasted actions. How much better was it?
Let's look at the 7B model again on ALFWorld L0.
Yeah.
GRPO had that awful 21.5% repetitive action rate, remember?
Yeah.
RLVMR, 2.3%.
2.3%, down from over 20. That's nearly at a 10-fold reduction.
Incredible difference, isn't it? And invalid actions, more than halved. 14.8% for GRPO, down to 5.6% for RLVMR. It just behaves much more purposefully.
It's the difference between flailing and actually thinking.
And critically, this efficiency holds up on unseen tasks. GRPO got worse on unseen L2 tasks, with repetitions jumping to 31.2%.
Right, the bigger models doubling down on bad habits.
But RLVMR's rate stayed much more controlled. It went from 2.3% on L0 up to 11.7% on L2. Still an increase, as expected for harder tasks, but way, way better than GRPO.
So it learns a more robust, generalizable reasoning process that doesn't break down as easily under pressure. It learns principles, not just paths.
That's exactly the takeaway. It's learning core problem-solving skills.
And surely a consequence of this better reasoning is better self-correction. Fewer loops means it's getting unstuck faster.
Absolutely. The drop in invalid and repetitive actions directly points to better error recovery. The agent isn't just blindly repeating failures.
Because of those rewards.
Yeah, the Explore reward pushes it to try something new, and the Reflection reward encourages analyzing why it failed and finding a corrective action. It learns to stop, think, and adjust.
There was that example with the soap bars, right? How did the RLVMR agent handle that compared to the looping GRPO agent?
It's a night and day comparison. The RLVMR agent was doing the task, find 2 soap bars, put them in the cabinet. It was progressing systematically. Then, at step 14, it had a little hiccup, a hallucination maybe, tried an ineffective action, examined soap bar 2.
Okay, a mistake. What happened next? Did it loop?
No. Immediately, at step 15, instead of looping or trying another random action, it triggered reflection. Its output was something like, reflection. Hold on. I failed to put the second soap bar in earlier. Need to double check my inventory first to make sure I actually have both before trying again, reflection. And then its action was inventory.
Wow. It diagnosed its own potential error and decided to verify its state before proceeding.
Exactly. Compare that to the GRPO agent trying to go to dresser 1 repeatedly. The RLVMR agent showed a much more rigorous, robust, almost human-like ability to self-correct and prevent wasted effort.
That's a massive step towards reliability, like
Yeah.
an agent asking itself, wait, did I mess up? Let me check. Real internal accountability.
It really is. And the benefits extend to training efficiency, too.
How so? Faster learning.
2 ways. First, the learned policies themselves are more efficient. They find shorter paths to the solution.
Fewer steps to get the job done.
Right. On that tough ALFWorld L2 split, RLVMR agents needed only 15.4 actions on average. GRPO needed 21.7, GGPO needed 19.4. That's a 20–30% reduction in steps.
And that comes from penalizing the redundant actions.
Directly. The exploration and reflection rewards teach it to be more purposeful. Fewer steps mean faster completion, less compute, fewer chances for things to go wrong in the real world.
Makes sense. And the second way, it's more efficient.
Learning stability. When you plot the average number of actions taken during training, RLVMR shows this nice, stable downward curve. It steadily learns to solve the problems in fewer steps.
And the baselines.
Much messier. GRPO and GGPO often show unstable curves. Sometimes the action count even goes up as they try more complex, but ultimately inefficient strategies. They flail around more during learning.
Especially on ScienceWorld, the paper noted.
Yeah. RLVMR's cold start gives it that initial grammar, and the dense rewards provide a stable learning signal, preventing those wild swings and inefficient loops from developing in the first place. Much smoother, more reliable training.
So RLVMR isn't just better at the end, it learns better and performs smarter throughout. Powerful stuff.
A very powerful combination, yes.
Okay, the results are compelling. But science demands skepticism, right? How do we know it's these specific RLVMR ingredients, the meta-reasoning rewards, that cold start doing the heavy lifting? Ablation studies are key here.
Absolutely critical. You take the system apart piece by piece to see what breaks. They did exactly that, testing on the challenging L2 split with the 1.5B model.
So first, what happens if you take away the meta-reasoning rewards? The whoa AMC condition without agent metacognitive control. No rewards for planning, exploring, reflecting.
Performance takes a big hit. On ALFWorld L2, success drops by 11 percentage points from 56.3% down to 45.3%. ScienceWorld drops over 6 points.
And what does that configuration basically become?
It's essentially just GRPO again, but with the cold start benefit. The sharp drop confirms it. You need to directly reward those beneficial reasoning processes. Outcome-only rewards aren't enough to guide the agent towards intelligent, efficient behavior. It just reverts to inefficient exploration.
Okay, so the process rewards are vital. What about the other side? What if you keep the process rewards but remove the outcome reward? The whoa AT variant, no final win-loss signal.
What do you predict? Rewarding thinking, but not caring if the thinking actually solves the problem.
Seems like it would just drift. Do lots of exploring and reflecting, maybe, but without any goal. Sounds disastrous.
You nailed it. Catastrophic collapse. ALFWorld L2 success plummeted to just 12.5%, ScienceWorld down to 7.8%.
Wow.
It perfectly highlights this energy. Meta-reasoning rewards shape how the agent thinks. But the final outcome reward is absolutely essential to direct that thinking towards the actual goal. You need both. Process without purpose is useless.
Like rewarding studying but never giving a test. The studying might not focus on the right things.
Exactly. It's the combination that works. One shapes, the other directs.
Got it. And the last piece, that lightweight cold start phase. Whoa, yes, it's only 200 trajectories. Seems minor. Is it really that crucial?
You think it might be minor, but nope. Removing it caused another substantial drop. ALFWorld L2 success down nearly 16 points. ScienceWorld down almost 8 points.
Why is that tiny bit of initial tuning so important?
It's not about learning the tasks themselves in those 200 examples. It's about bootstrapping the agent's ability to even generate the meta-reasoning tags correctly, to follow the required syntax, the grammar of thinking.
Without it, it doesn't even know how to speak the meta-reasoning language.
Especially for smaller models, yeah. They often fail to produce outputs that the system can even parse if they don't get that initial grounding. The whole RL training becomes unstable and can just collapse.
So it's an incredibly efficient way to lay that essential foundation for the structured reasoning needed later. Okay, these ablations really drive it home. RLVMR works because all these design pieces work together.
Precisely. Each component plays a critical, non-redundant role.
So let's zoom out. What does RLVMR mean for the bigger picture? We're talking about building genuinely intelligent AI. It seems to hit some core challenges in RL, right? Like sparse rewards.
Absolutely. LLMs as agents are transformative, but that sparse reward problem, only getting feedback at the very end of a long task, has always been a major hurdle. It makes learning slow and inefficient.
And RLVMR tackles that head on.
Directly, by injecting these dense process-level rewards based on verifiable reasoning steps, it provides feedback throughout the process. We're not just hoping the agent learns something useful. We're actively rewarding how it thinks step by step.
Which leads to agents that are.
Not just successful, but robust,
Yeah.
less likely to break. Efficient, using fewer steps. And more interpretable because their reasoning is explicit in those tags. They learn to solve problems intelligently, not just by luck or brute force.
So for you listening, the so what is potentially huge. If you want autonomous systems you can actually rely on in complex situations.
This is a significant step forward. Think of robots in warehouses, complex process automation, maybe even AI assistants helping scientists. If these agents get stuck in loops or can't handle slight novelty, they're not very useful, maybe even dangerous.
But RLVMR offers a path towards more dependable agents.
Yes, by instilling this rigorous, verifiable reasoning process, they become more reliable, better at error recovery, more adaptable. It builds confidence for real-world deployment. It's about designing intelligence that actually works robustly out there.
A really exciting direction. It feels like we're genuinely teaching AI to think more like humans do, with that metacognitive layer. But the paper mentions future work in multimodal domains. Vision, audio. We've mostly talked text environments here. What happens when you add noisy, real-world senses?
That's a fantastic question, and it points to a major challenge ahead. The paper doesn't really dive into this, but it's critical. How do these structured meta-reasoning tags, and more importantly, the rewards for them, translate to real-time robotics?
Right. How does an agent reflect on why it drops something when it has continuous visual input, maybe slippery physics, uncertain lighting?
Exactly. The observations aren't neat text descriptions anymore. They're streams of pixels, audio waves. Do the tags need to become more complex? How do you reliably verify if an explore action in a visual scene was truly novel or just looking at the same thing from a slightly different angle? How do you reward planning when the plan involves complex physical interactions?
It feels like the complexity explodes.
It does. Bringing this kind of structured, verifiable reasoning into the messy, high-bandwidth world of multimodal data is a huge but incredibly important next step. How do these cognitive functions manifest, and how can we reliably reward them in dynamic physical interactions? That's a key area for future research.
A challenging frontier for sure, but equally exciting. The path to truly autonomous AI is definitely ongoing, but RLVMR feels like a really solid step towards making AI think more effectively, more robustly.
I agree. It's about building agents that don't just act, but understand, adapt, and learn from their own thinking process, a fundamental shift.
Well, that brings us to the end of this deep dive. Thanks for walking us through that.
My pleasure. Fascinating work.
And for everyone listening, to stay updated on the latest AI and ML research, and for more technical discussions like this one, do check out our webpage. The link is in the bio. We'll be back soon with another deep dive into what's new and impactful in AI.